Okay, and then it should work out nicely, I think. The 3 to the ends are going to cancel. The 2 to the ends are going to cancel. So what we're going to be left with on top, if I can squeeze this in, is the 2 times the n plus 1 in the numerator. Right, 2 then plus 1, and then in your denominator you will have this 3 and the n squared. So if you simplified it while I was getting the recorder set up, this is hopefully what it broke down to. You can distribute your 2, right? There's no harm in that. Either way, it gives us a nice simplified fraction that we can now find our limit of. Power of 1 in your numerator, power of 2 in your denominator. Yeah, did I screw something up? Everyone's looking at me like I'm crazy. Oh yeah, did I forget the squared? Good, because that's going to affect our answer. Yeah, so this guy should have gotten dropped down, sorry. That's why it's nice having people in class. And everybody looks at me like I'm crazy. I know I screwed up. So then now the degrees are the same. So n squared and n squared. So now we look at their coefficients, and that should have been 2/3. Is that what we all got? All right, good. Keep these straight now in a P series and in a ratio test. Both of these are considered the P, but in one instance being less than 1 is good, one instance it's bad. So with this one here, yeah, this is the last one on this page. Let me just create some space over here. With the ratio test, that means that this converges. You state your test. So tomorrow on this quiz, this is pretty much the order. Does it converge or not? And if it's absolutely conditionally, we need to add that. This one, there's not alternating, so we don't have to worry about the absolutely conditionally. Then you're going to state the reason we did it, or the test that we did, and then justify that test. So in this case, we ended up with a P that's equal to 2/3, which is less than 1. All right. And as the ratio test goes, that's converging. All right. So think about it, Aaron. It might go better because you have all of these in front of you to use. All right. Number 9. Again, natural logs, as a general rule, and almost anything that we do, if you can simplify these, you really want to create a most simplified expression to work with. So in this case, we can definitely simplify this a little bit before we dive too far into this. The natural log of n in the numerator you can't do anything with, but can't we take this 2 and move it out in front so that this is a 2 ln and then all of that squared?
Did you want to change that outside exponent to an n?
I did want to switch that to an n. Good call. Yeah, make this an n. What we then see is these are going to cancel, and we now have an alternating series of just 1/2 to the n power. All right, so been doing most of them. Write down what you think. So we got a quiz on this tomorrow. The first one's kind of hard, like this is the first time we've seen this. But once we get to this step here, this we've seen now a handful of times. So write down what we think we would say here. All right, let's see where we're at. First things first, we should see that it alternates. So when we did these yesterday, we talked about how if it alternates, it really loosens our conditions to converge. As long as it's alternating, which this is, then the non-alternating part, so this here, just has to go to 0. Does that go to 0 and goes to infinity? Yeah. If you can't see that the way it's written, if we wanted to simplify that a little bit, isn't 1 to the n just a 1. So the numerator is always going to be a 1. And then your denominator is a 2 to the n. That should hopefully be much more obvious then that the exponential function is on the bottom, a constant on top. So we're alternating. This very clearly goes to 0. So this definitely converges. Because it is alternating, though, we now need to add the little descriptor here. Is it conditionally or is it absolutely? So then that now basically means just focus in on the non-alternating part and basically ask either this version or this version, would this be okay if it wasn't alternating? So if that was its own problem, is that a series that would converge? Yeah. So that means we converge absolutely, that if we did the absolute values of all of them, which means we're not alternating basically, that guy is totally fine by himself. The reason he is totally fine by himself, again, hopefully is what we've been doing probably the most of. This is what kind of a series of those 5. Geometric, right? So this is a geometric series. Here. With a ratio whose absolute value is equal to 1/2, which is less than 1. I can tell you the ratio test is pretty reasonable as well. If you did a ratio test with this one, that would work pretty quickly. That group quiz, usually when we take that group quiz, everybody tries the ratio test all the time because it's very straightforward. It takes a little bit of work. So the ratio test would have been pretty reasonable. So either one of these would work. To me, this is the much quicker and more efficient route. Okay? All right, good with that? Yeah.
Alternating series here for that one.
So if all in last year it was nice because that's all they asked, but it says determine if these following series converge absolutely, conditionally, or diverge. So in general, if it converges, if it's alternating, we want to state if it's converging absolutely or conditionally. Okay, for all of them. So because this one was alternating, we want to say this for sure, but we also then want to add in if it's absolutely or conditionally.
Okay, so if it didn't ask that part, but then you can just put it.
Yeah, and there's something we're going to do in the very next section where it just needs to determine if it converges or not, and then we would be able to say converges just because of the alternating series theorem. But with these, you want to then state if it's conditionally or absolutely. Okay, who was that? Who was asking at home?
It was me, Ran.
Was that the same question, or do you have something else?
I didn't exactly hear the other question, but I was just wondering because when we did the alternating series before, we learned that it had to be to the n plus 1 power. Is that not necessarily? Does it not necessarily always have to be like that?
Are you referencing this right here?
Yeah.
No, as long as it alternates. So both a -1 to the nth power, really a -1 to n plus 1, n minus a 1, as long as this overall is going to alternate, it doesn't have to be an n plus a 1 right here. All right.
Okay.
In fact, as we go to number 10, since you kind of brought it up, I was going to have you try this, but it's a good talking point now. There's no -1 to the n or a -1 to the n plus a 1, but remember how we talked about this is another way of doing an alternating part. So if we were to really go into this one, this is also an alternating series. All right. So we could, if we want, you don't necessarily have to, we could kind of pull this out and then write this as 1 over n root n. This will also then, let's kind of go through our process. Because it is an alternating part, and then again, it doesn't matter if it's -1 to the n, -1 to the n plus a 1, or we do it with the cosine of pi n. This is alternating. So then this just needs to go to 0, and it does. The faster growing functions, since the numerator is a constant, is in your denominator. So this will converge. But since it's alternating, we need to then add that descriptor. Is this guy good to go on its own? So write down what you think. If you think this converges on its own, you would say absolutely. If you would say it doesn't converge on its own, then it's conditionally. Let me give you a little hint, some algebra stuff, and then see when I write the little hint here if it still is going to mesh with what you were thinking originally. This is an n to the first being multiplied by an n to the 1/2. So this could be simplified to be n to the 3/2. And now see what you think. It confirmed what you were thinking in the first place. All right, so this guy right here, whether you did it here or the simplified version, if this was all by itself, would this be something that converges? Daria says yes. Why do you think yes, Daria?
P series greater than 1.
Good. This is a classic P series. You have a 1 in the numerator, even though it doesn't have to be 1, it needs to be a number, and then you have an n to a power, so this is your P right here. And so let's go ahead and do P series. And then our P was equal to 3/2. And in the P series, if your P is equal to a number greater than 1, that means it converges. So she said it's a P series, P equals 3/2, it's greater than 1. That means this guy works on its own. So that is why we would have to say this is absolutely. Even if it was all positive, it would still be good. Okay. Oh yeah, we probably want to do one more of these for sure. And I think there's one on that test or quiz. So let's hammer out one of these guys. Although it looks familiar. Yeah, let's do it. It's alternating. Now the test to see who watched this and understood this. Since it is alternating, the only thing that has to happen is the non-alternating part. So what I have highlighted in blue, this has to pass the n term test and go to 0. So if I compared an n factorial squared to a 2n with a quantity factorial, does a 2n quantity factorial go faster than 2 factorials together? Mixed reviews here. All right, let's see who watched that video. So the coefficient of a factorial makes factorials grow faster than an exponent. Probably very much, again, counterintuitive. So a coefficient for that n with a factorial will grow faster than an n factorial. Okay. So this does pass the n term test, which means this is going to converge. Okay. That's something you want to know. Don't put a comma though, because it is alternating. So now we need to state if it's absolutely or conditionally. Factorials are pretty straightforward. It's going to be the ratio test 99% of the time. There's really not many ways around this. So if we go through with our ratio test, you don't necessarily need to worry about this guy when we do the ratio test. What we're really just testing is this, right? And this is what looks familiar to me. I think we just didn't do it as a alternating series. So that we have 2 n factorials. So that means I'm going to get n plus 1 times n factorial twice. You know what? Let me not skip that step. Sorry. Not quite there yet. So we have an n factorial, n plus 1 first, and then it was squared, so you'd have 2 of them. So hopefully that makes a little more sense. So that's our n plus 1 in the numerator. In your denominator, your n plus a1 is here. And then we're going to divide by the original, which is the same as multiplying by the reciprocal. Then I'm going to add maybe an extra step for some of you. I'm just going to rewrite pretty much everything. Except this, I'm going to go ahead and distribute and write this as a 2n plus a 2 factorial. And then everything else I'm going to rewrite. If you can kind of already start canceling stuff, feel free, but we'll be pretty thorough here. Then this n plus a 1 factorial, since we don't know what n is and when to stop, That would go on forever. So we could do n plus a1 and then just start subtracting a 1. But I'm going to stop it at n. So I'm going to subtract 1 to get n. And then I'm going to put a factorial behind that. And the reason I would stop there is because I have an n factorial in my denominator. And that's going to allow those to cancel. Same thing would happen with this guy. So this one here, I'm going to do n plus a 1. I'm going to start subtracting 1. But once I get to an n where I can put a factorial behind it, I'm going to stop there because I have 2 n factorials in my denominator. And then not only would those n's cancel, but all the subsequent terms represented by the factorial would also cancel. All right, next one. That 2n plus 2 factorial, that would mean we start at 2n plus 2, and then we're going to subtract 1 to get 2n plus a 1, and then technically we keep subtracting 1 over and over and over again. But if you notice, we have a 2n factorial here. So once I get to the 2n portion of this, I'm going to stop and put a factorial behind it so that I then match it up with the 2n factorial that I had in that numerator. Then stuff starts to cancel. So the 2n factorials will cancel, the n factorial, and a lot of n factorials canceling. If you remember, we did do a version of this yesterday. I pulled out the 2 from this one, and then this is an n plus a 1. We factored. So then we see an n plus a 1 would cancel. So what we finally end up with is this. Find your limit as n goes to infinity, so 1/4. In the ratio test, being less than 1 means it converges, meaning this converges whether it alternated or not. So we come back up here, it converged absolutely because we did the ratio test. And we found that our p was equal to 1/4, which is less than 1. Okay, we're going to do another fact. I want to make sure we do one more of those in that little quiz here in a second. All right, number 12. 12 would be a nice one, hopefully. So do that one. All right. What we should notice right away, it alternates. So then what we have to determine first then is the non-alternating part. This part here just has to go to 0. And if it does, then it converges in some way, shape, or form. All right, does this non-alternating part go to 0? No. So right away, we can say this one diverges. And then what we determined for this is the nth term test. And then Aaron, for those who were at home, asked if this quiz usually goes well, and I said, no, not really. But here's one of the mistakes that we can kind of get corrected right now that I try to talk about every year. In term test, we would say the limit as n goes to infinity for our general term, and then you just want to be careful because this is where people give away some points. We don't want to put a 1 right here. The 1 is just this part of it. If we actually start listing out the first term and then the second term and the third term, aren't they also alternating? Which means the overall limit of all of these sequence of numbers here is going to what? Doesn't exist. So we would say that that limit does not exist. If the alternating part wasn't here, then we would say that it's a 1. But the alternating part just means we're bounced back and forth between 1, -1, 1, -1, and that's why it doesn't exist. Okay? So that's something that hopefully we won't do tomorrow. Okay, go to the quiz review, because first things first, I was kind of comparing these. And I had made some adjustments. I'm pretty sure I gave you a different version, an older version. I like my version, my new version better. So go to your number one. Your number one, I prefer you put the one that I have. So make this your number one. So cross out the one that I currently have there. Put that one in. Big. All right, we all got that one. All right, 2 is good. 3 I did not change. 2. Yes, good catch. Yeah, add that to yours. Good catch. All right, 3 is good. Number 4, don't concern yourself with the alternating part, so just cross that out. Oh no, yeah, I want to cross mine out, actually. All right, that's good. Doesn't matter. You can if you want. It won't impact the answer. So either way. Your 6 is the same. Your 7 is the same. All right, your 8s, change to that. So also change your 8s. So change it to this one. That's one if we have some time, I'd like to do. All right, number 9, change to that one. Yeah, let's get them both on there. There. Because I'll probably key this up and I'll send it out via the remind, and then you can kind of have the key available to you. I thought maybe I had put it on in the packet, but I saw that's what I was really looking for this morning when I realized I printed out a different version than what I have ready. All right, we got all those. So I'll write out the key and send it out. Say that one more time.
1.
Number 1? Yeah, let me make sure 10 is good. Yeah. And then number 1 should have been that. And then I want to do one of the factorials here. There, got it? All right, so let's do one more of these with the ratio test. All right, Brian, which one looks the most fun, Brian? 8, I know they look equally fun.
9 looks fun.
Okay, number 9. So let's go to number 9, and let's see if we can kind of get through one of these. So actually do the first step or two. See if you understand how we're doing the n+1 series, dividing by the original, simplifying this so that nice things happen for us to reduce this down. All right, and let's see where we're at. So our first priority with this n+1 series is the n has to get increased by 1 first. So the n becomes an n plus a 1, and then I would do the factorial. When we go to the denominator, I have to increase this by 1 first, and then everything else, order of operation wise, behaves normally. So that n becomes an n plus a 1, then I would multiply by 2, then I'm going to add the 1, and then I'm going to do the factorial of all of that. So that is why this here would break down or simplify to be that 2n plus a 3. All right, good with that so far? All right, so then from there, we want to clean this up a little bit. So the first one we've done. So we've already talked about how an n plus 1 factorial, if we want to clean that up, we could continue forever. But if I notice that I have something that it would eventually reduce within my denominator, which in this case is an n factorial, just subtract 1 one time, and let's not continue on like this forever. Let's just put a factorial behind it to show that it does in fact carry on forever, but we know that we can stop it with that factorial. And then that's going to cancel out now nicely with this factorial. So when we look at this 2n plus 1 factorial, you don't really want to do anything with this one yet, because if we have a 2n plus 3 factorial, this one would start with a 2n plus 3, and then we start subtracting 1 each time. Wouldn't we want to then stop at the 2n plus a 1 and then put a factorial behind that, saying that we do get more terms after that, but it would be the same exact terms as the 2n plus 1 factorial that I have in that numerator. All right, we all see that? Then nice things happen. These 2n plus 1 and all the subsequent terms cancel. Same down here. The n and all the terms after the n cancel. And all you are then left with in the numerator is an n plus a 1, which we could reduce, I suppose, because you could pull out a 2, but not terribly urgent. And then we get a 2n plus a 3 and a 2n plus a 2. Yeah, let's go ahead. So this, I'm going to pull this out, n plus a 1. And then the n plus 1s will cancel. So what we end up with is 1 over 2 times 2n plus 3. Now that's really, really easy to identify what your limit is as we go to infinity. So if you had gone all the way through that and you got your ratio test p-value to be a 1/4, then that's pretty good. All right, having just kind of went over this yesterday, there's some weird stuff with all those factorials. So this thing then ultimately converges. Oh yeah, see? What should it be, Brian? Good. Yeah. Nice catch. Yeah, it should be a 0 for sure. We have bigger degree in our denominator. All right, should be a 0 there. The other one was 1/4 is what I was thinking there. So yeah, it's definitely a 0. So this converges with the ratio test with a p equal to 0, which is less than a 1. All right. Now, since you're here, let's do this real quick, then I don't have to worry about this one tonight. Tell me what happens in A very quickly. We've already now talked about it. It's not alternating. So if we do our nth term test, is our faster growing function in the top or the bottom? Top. If I have factorials, what determines if that's going to grow faster is the coefficient. So this factorial has a coefficient of 1. This has a 2. So this actually diverges right away. You can do the ratio test, but I think we just saw ratio tests with factorials can be a lot, right? We just did one of these and it's all this work here. So if we can recognize right away that this diverges because of the nth term test, then you're saving yourself a lot of hassle and time. And we would say the limit as n goes to infinity is infinity because the faster growing function is in the numerator, okay? I will key this up. I will send this out. And some of these you could do 2 or 3 different ways, so I'll try to put all of them just in case you choose a different option. And then if you have any issues, just see me Friday, see me tomorrow morning, second period, and then we can try to work through anything that you might have. You guys will, and then so